Hi everyone, I am Kamal Hakimzadeh. I would like to present our paper IMITA, which is Imitation Learning for Generalizing Cloud Orchestration. This work is a collaboration between KTH and Nokia Bell Labs. What is the motivation behind this work? So as we know, more and more large corporates and companies, they are moving their computing clusters and cloud applications to the public cloud providers, and they need to update their applications very frequently. They usually allocate a team of engineers and cloud experts to do this work. And this work, this update has to happen very frequently. And in the end, it becomes very expensive for companies. On the other hand, cloud providers, they want to streamline the process for their customers. They want to create the orchestration techniques that their customers can can use it off the shelf. The way cloud experts work or do the orchestration, they usually use application-specific indicators that we call them KPIs in this paper. KPIs have different behavior on different cloud stacks. If you deploy the same application on two different underlying platform or resources in the cloud, the indicators, application indicators, they show different behavior. Cloud KPIs are inaccessible for infrastructure as a service cloud providers, which in case of large corporates, they usually use infrastructure as a service. On the other hand, resource utilization metrics are universal and can be used everywhere, but they are too low level to create any generic method on them that can work in different scenarios. What is our hypothesis? Our hypothesis is that resource saturation footprints are transferable across cloud stacks. So any auto-scaling or in general, any orchestration mechanism that is based on saturation footprints can be easily transferable. This picture shows the idea. So on the left-hand side, we have when applications show some bottlenecks in the performance in the indicators. It's basically a combination of what workload, what application, and what platform is running. And those examples of bottlenecks, they always have some counterparts or representation on resource footprints, resource utilization footprints. And so these utilization footprints, they are they may cause different types of bottleneck, the same utilization footprint. So if you identify through one performance bottleneck, if you identify utilization footprint, then we can use it in different for different performance bottlenecks. What is imitation learning that we are using? Imitation learning is problem solving by making sequential decisions or sequentially making decisions. It has a setting containing environment, it's a set of states, and it contains a set of feasible actions that we can take in each state. Then these actions are taken according to a policy, which is a function from state to actions. And then based on terminology, there are a sequence of state and actions. It gives us a trajectory. In self-driving car, we can see one example of application of imitation learning. An expert shows in trajectories by driving a car, and the machine learning model trains the policy of the expert. And for those corner cases that there is no data, usually the model fails in those cases. So the goal of imitation learning is to train an imitator policy from an expert policy that they can imitate the expert. One implementation of imitation learning is the algorithm that is called dataset aggregation, or Dagger. It works based on the fact that all imitation learning problems are convertible to supervised learning problems. This is the algorithm, and the algorithm or Dagger takes as input the expert policy and a classifier. So these are optional or let's say portable, can be any classifier algorithm can be used. It trains an imitator policy in iterations, and it bootstraps from expert policy on a small data. Then it lets the imitator basically steer the system, but the expert is also there to annotate the mistakes, and the imitator learns from its own mistakes. This is the idea of Dagger. How we incorporate Dagger or imitation learning in our solution. So this is our logical solution that is based on a classical feedback loop of cloud control. So in the feedback loop, we have a system that we would like to control, and we have a controller that basically controls the system based on some feedback that it receives from the system. So this goes in a loop, and the controller always controls the system. But what we do, we separate between the type of feedback that we give to the expert versus the type of feedback that the imitator can see. So the expert demonstrates its trajectories in a performance space or KPI space, but the imitator learns in resource utilization space, the same thing. What is the practical considerations here that we need to take into account? First of all, the exploration space is too large. If you want to make a generic model, we need to produce a lot of examples for many. It's almost impossible. The expert is, the other one is that the expert is inaccessible after the training phase. We usually don't have access to, in production, to the experts, that they can produce a lot of examples. How Dagger works, Dagger is based on the fact that the trained model steers the system and the expert annotates the mistakes. But the way we do it in IMITA, the expert labels in the training phase, but the imitator decides what is the next step. We need to have some sort of smart data collection and training for quick convergence. That's our algorithm, IMITA. And we need also to have some sort of difficulty metric to choose what is next to be explored by the imitator. This is the main algorithm of this paper, boosting heuristic. It makes a call to an expert by giving a configuration or subpart of a large configuration space. It aggregates the collected trajectories. So basically, for that configuration, the expert explores the configuration, that configuration space, and it produces some trajectory. So we aggregate the collected trajectories in a training set, and we train and we choose what is the most difficult configuration to be explored next. We continue until the desired accuracy is achieved or max iterations are consumed. This is the system overview. We implemented a system for our algorithms. So this system, this is the architecture of the system. It's based on two big pieces. One is the YCSP. We made a major modification in YCSP, and we use a Linux container-based application launching in a Docker Swarm cluster. So it has adaptable traffic distribution, and the measurements, we do the measurements on throughput and latency, and a lot of detailed metrics. So what is the expert that we use? As we know, human experts are expensive and slow to be used for this kind of training. In real world scenario, samples are imbalanced. So even if you have an expert, in a real world scenario, most of the time the system is in a healthy and unsaturated situation. But as soon as it enters a saturated state, the expert will take an action. And we don't have so many examples of saturations. So the samples are very imbalanced between saturated and unsaturated, and that's not going to give us a good result in a machine learning model. We created an automated expert. It's explained in the paper, the details. But the automated expert controls the training, controls the system in two phases: training phase and basically sampling phase. It generates traffics and it labels the samples. And here how we evaluate our algorithm. So first of all, we run the system that I explained in on 7 servers with 32 core CPUs and 132 GB RAM. And we use Cassandra as our application. We scale it from 1 to 20 container instances. We run it for 60 hours. The entire cluster, and we use 6-second measurement intervals, which gives us 36,000 training samples. And we use the random forest classifier, which because first of all, our algorithm is agnostic against what classifier can be used. And also we choose random forest because it's less prone to overfitting. What is the configuration space? So we implemented a system, the implemented system is highly configurable because we can use different types of applications and we can give them different amount of resources. What we do for our evaluation, we choose the auto scaling scenario with add one resource and do nothing type of actions or class labels. We have 3 container flavors, 2 CPUs, 4 CPUs, and 6 CPUs, and 3 workload mixes, 100% read, 100% update, or 50-50 mix of this. This gives us 9 configuration sub-configurations with different levels of difficulty. We'll measure the difficulty based on the difficulty metric that is explained in the paper and its algorithm. Each configuration or each cell gives us a 1 trajectory and 20 sub-trajectories inside 1 trajectory per scale, basically. So we would like to see what is the learning curve and how quick imitator can learn to get to more than 80% F1 score. We use this auto-scaling scenario with 2 actions, and we compare boosting heuristic against random sampling. And the reason being that random sampling is, in general, it's a good method or sampling method to when you want to have samples, representative samples from the entire space. And that gives, that is very highly, it gives us a model that is very generic, basically. We run the cluster 60 hours or equals to 216,000 seconds to collect all the trajectories. And this is the result. We zoom in from 60,000 seconds to 140,000 seconds because in the beginning, all the algorithms start from the very low accuracy because they have very small data. And then in the end, when they have all the data, they all converge to the same thing. So it's good to see what is the path they take to go from low accuracy to the high accuracy, and when we can stop it. So we measure the median and variance of F1 score. So as we can see, boosting could be stopped at 26 hours, somewhere in the middle, as soon as it gets higher than 80. And for the same F1 score and the same variance, we should run the random sampling. We can stop only in 36 hours and in the 50th hour. So basically, random sampling requires 34% more data and 100% more data to become as accurate and as robust as boosting. And we also would like to see the efficiency as elastic controller when we use IMITA as an elastic controller. We generate real-world traffic patterns for 2 hours and 40 minutes each. It's a read and update mix of workload on 5 core containers. And this type of container is not used in the training, so this is a new setting that we're going to test it for. The figure shows the results. I'm not going to go too much into the detail, but you see the big spike, dual phase, large variation, and a steep drive phase types of workloads that are important. And the first one, the first row shows the throughput of the arrival rate and the service rate. And then the second row shows the calculated adaptation based on a Bungie benchmark for elasticity. And the last one shows the SLO violation. So as in summary, the service rate matches the arrival rate very much all the time. We only have 2% unit of resource 2% of a container, under provisioning in steep phase in the last one. And we have over provisioning because we didn't implement a scale in action, and that was for some practical limitations that Cassandra had, and also that the workload is the throughput is non-monotonic all the time. As we add more resources, we don't necessarily get more throughput. So we would like to put the magnifier on why we get more over provisioning. Is it because the model doesn't work well? And in that context, the main source of over provisioning is our false positive actions. So we evaluate the number of false positive actions out of 1,600 actions that we take for entire run. And these are, we compared 4 different scenario policies here: single metric based on CPU, rule-based CPU and network, decision tree imitator, and random forest imitator. Single metric and rule-based are carefully designed that they can give us the best result based on our analysis of the data. And single metric performs better than the rule-based, 4.3% false positive against 9% in the rule-based. And that means that not necessarily always the more complicated rule-based system, they give better result than the generic simple one. And the decision tree gives 3% false positive, better than the rule-based, better than the single metric. And the random forest has only sub-percentage false positives. How it can fulfill SLO. So we choose latency here because it's very important KPI for applications in the cloud. And we know that latency distribution should have short tails. That's usually reflected in SLAs. Our training is based on throughput. We trained the model based on throughput, but now we evaluate it for latency. We choose latency 99 percentile, 90 percentile of 300 milliseconds and 550 milliseconds. We calculate violation for targets. And this table shows the results. In general, most of the cases has sub-percentage violations for the tail latency and less than 5% violations in the worst case scenario. With that, I would like to conclude my talk. We introduced the concept of imitation learning for cloud orchestration. We presented an automated and practical solution to create accurate machine learning models. We contributed a heuristic that reduces time, resource spent on the data collection. IMITA produces generic ML models that can be applied to unseen settings. I would like to also to give some future direction we would like to study the method for a wider range of scenarios and applications, try other techniques to incorporate human expert in the loop, try to decrease the data amount for data collection even further, and study the technique on noisy environments. With that, I finish my talk. Thank you very much for listening.